I am continuing with where I thought I had left off, and also get back to few of these fundamentals. Do not worry about it, I have taken a picture of it. This is the small sheet metal part which my colleague in the workshop has fabricated. The issue being, it needs very complicated and highly skilled operations. These highly skilled operations, if you remember, I do not know whether I have shown you or not, all for just making this small timer. They have gone through just a large number of this thing. I will quickly go through this. It is nothing, it is just that saying we can make the timer in the conventional way. Now we will take it to the workshop. I was just showing how it is. The difference being, in this case, instead of going through that elaborate calculations and so on, we have made a template, stuck it on a bit of raw material, and we are going to make all these things as they are. This is what I had shown you. This particular, this is the blank which already, if you see there at this point, this is the blank which he has already kept it on the machine. This machine was used for making the blank, it is kept here. Then we have something here, and of course this you know what it is. The video follows afterwards. Now, one thing you have to notice is that 45 degree or angle thing is very easy to generate in CAD, which by, if you want to use this, it is not easy to do the marking on these things. Standard basic marking, the next what I call demo will show you that there is no issue about the horizontal lines, and vertical lines also is there, no issue. However, if you want to make lines of some arbitrary or derived due to procedures in laying out which have come, it is not easy to make those things, because see, it looks here, if you look here, it is not easy to even read these things. And this one in fact has a provision for attaching a lens, lighting, and one has to be really sharp, and tremendous amount of calibration is required to see that this marking edge, okay, this is a marking edge, this marking edge has to exactly coincide as per the scale that it shows here. Not easy to read, is not easy to make, everything is not easy. In contrast, if we were to just take a simple printout in your any printer, the normal printers we have at home is okay, even in the office, the accuracy is about the same depending on the condition of the printer and all that. A minimum of 0.1 to 0.2 millimeters you will get over the total length of 290 millimeters, actually it is 297, and afterwards once these are marked here, you see here there is a bending line, then there is a slot that is marked here, and very easy for us to follow these things. I will say if it can you see here, there is something here, very tiny device. Any small this thing can be done, and see there he is trying to set up the machine. After that necessary reliefs have been made, there is a small relief here, we can see it here. He has used a normal hacksaw, and the critical thing we need to observe is the wanted limb versus the other limb where things can change a bit. And same thing here, if you want to ensure that these limb dimensions and all come properly, it is very easy for us if you have a template, else you end up having to mark it. You see here quite easily he has done it. Next what you call set of slides will show you this, and finally he is measuring whether the dimensions are okay or not. This being the first phase, let me be honest, they were not to my satisfaction. So, this is not encouraged, but still one part which comes last, the final cover, he has tried to take a equivalent sheet and then he has tried to bend it. You have seen it here, he has tried to cover it and made something which is okay, tolerable, but not to the standards I expect. Sin here didn't come out well. And even here, if you say there is a little bit of projection and the radii didn't match, and probably quite a bit of stuff. Just to show you the conventional way and the difficulty in making it, I thought I will present this to you. While it is also useful in case you really have access to a workshop or a professional shop and you are one of those people who enjoys highly technical items. Saying if you are a serious hobbyist or you are one of those I will say hackers who enjoys taking things under control. Point being here is somebody has to give that person an actual drawing of the part we want. So, I made a drawing of this part and it is a part drawing. I will show you back at where the drawing is, then probably you will appreciate it better. Let me go through. See here. If you see this here now, I wanted this limb to be approximately something here and something here. And unfortunately, things like this, I wanted this much, that much does not make much sense to a person who has to fabricate it as per your instructions. So, easiest way for us is to make a sketch. You see here, this is a sketch saying this limb I must have it 20 millimeters. And in the case of production, we also had a what is called a tolerance and a fit and a allowance on this. Same thing, this limb has to be 50 and this limb has to be 30. Now comes the important aspect of what is called how to calculate bend length. So, you see here, either way I go, I end up with a very peculiar 20 plus 30, 50 and 50, 100 millimeters. We know very well that it is probably not 100 millimeters, but then we also have a small thickness here. Can you see here 1.6 millimeters. So, now how do we carry out this calculation? So, traditionally what is being done is the internal dimensions are added up. This represents the 20 mm limb, this represents the 50 mm limb minus 2 thicknesses, and this represents the 30 mm limb. These are added up, and added to that a factor called the added bending allowance is given to that. In our parlance we call it Z because we are used to it. So, for that depends a lot on thickness of the material and how it is going to be clamped inside, the minimum bending radius that can be achieved safely, and this is a empirical constant. It depends very much on the type of material, the what do you call various other factors very much related to how the material gets squeezed in between, what is the direction of grain, what is the hardness treatment that has been given to it. Soft materials behave differently from brittle materials. In the end, we do have a beautiful piece here. Can you see something about it? If you see carefully, this piece does have an internal radius, whether you like it or not, depending on how we have clamped it, plus a thickness. And if you just take the internal dimension will be starting from this point, internal dimension will be starting from that point. Alternatively, if you take an external dimension, so there are two ways of doing it. If you take the external dimension, there you have seen total will come to 100 millimeters, and then you have 94.7. So, 100 minus this 94.7 will give you a deductible allowance. So, that is a lot of difference, have you seen here. So, it will come to 5.3. So, which will come to approximately 2.65. So, we need to deduct 2.65 from both these items. Some places they follow such things, but in our case, because of the issue about clamping it, which I am going to come back to it, you see here something, you see a designation here. The designation here shows that this part is clamped inside the machine, and here it says in another way, no, this part is clamped inside the machine. I will come back to it later. Using all this, and we traditionally have been using this 0.56 is related for a 1.5 millimeter material with an internal radius of 0.5 and done in our folding machine, where the length that is not to be altered will be inside the clamp, inside the fingers. So, instantly if you see, if you add this to this, you understand, if you add 18.4 to this thing, it will come to approximately 18.96, which in some other context it makes sense for us. But you see here, though it says internal 18.4, something else is marked here, 17.9 is marked here. So, why is 17.9 marked here? This particular thing is related to the way our machines work. We have a finger which holds the immovable part, then after that the internal radius is added to that. So, if you say internal dimension minus that 0.5, we need to mark a line here. So, that is how it has come. So, we have an internal dimension of 18.4 minus 0.5, 17.9 is marked here. Advantage of this is, now this line is used for clamping it. Now, I will get back to this. You see here we have a developed length which has been calculated, and he is trying to shear it to the necessary developed length. This is the open thing, and mind you, there are fingers here also which clamp it, and much more important is there is a straight edge and a backstop. Right now the backstop has been what you call retracted. Then after that, if you go here, you see here, this is the machine which is at the back. After carrying out all the necessary markings and calculating the length, it has been fed to the machine, and this is the wanted piece which we want, which has come out of the machine. So, he is just picking it up and is doing various things, including this particular thing is called deburring. So, unless the machines are in what you call some new what you call laser cut machines or something, traditionally a burr is always formed. So, here we have a scale or a straight edge. In this case, it is a damaged thing, hence you see this red thing saying do not use it for measurements, and he is using it to make sure that there are no burrs on that. Now, sorry for sort of going through in a very funny, very quick thing. The point which I wanted to make right from the beginning is, after having done all these things, the most important is trying to make a marking. So, what we wanted to do is mark it here using a vernier height gauge. Vernier height gauges are normally used only in very accurate work, but the problem is everything depends on how well this bottom, it is a stone, it is a granite stone, how well it is maintained, how well it is lubricated and kept, and something equally important is how well is this marking edge maintained. Now, you see already it has a thickness and it is already showing a thickness. So, it is no longer a zero thickness line, and not a very comfortable way of trying to handle it. See here, the operator is forced to tilt it, take it off from the stand and try to look at it. Is this how it is? Not the best practice, but we hope things fall, and then some of you who belong to India will see what it is. We believe in somebody to take care of it. So, here what is done is, normally the proper way is it should be at an eye level and you should never take it off from the surface. Now, with these restrictions, it is not easy to actually read and mark things. See here, he is trying to point out to me saying, sir, you say this is the one, and eventually marking is done here. Can you see here? This is what I was trying to show you. Not easy to make the marking, but it does get done. Somewhere all the pictures are there, a larger thing. I'll get back to that and show you again. Sorry for this thing, because I am forced to go back and forward. Now, having sheared this machine, having done the marking, we now go on to the next operation, saying we have to get ready for bending. You see here if you see, this is a folding machine, and there is of course a long taper, and then you can see these two lines are there, and this is the clamping finger. What that clamping finger does is, it holds the material underneath. So, my colleague the operator is trying to show me how to move the finger back. To move the finger back, he is supposed to give that 0.5 millimeter plus one thickness of the material. So, this is the thickness. After that, he is visually is very what you call skilled at that 0.5 millimeters thing. So, he is now, that is the finger which is clamping. You may not be able to see the line. This material is now under the finger, that clamping finger. Now, you see here, maybe you will be able to see a little Now you see here, you see what he has done here is, this is the thickness of the material, then that 0.5 millimeters, total approximately 2 millimeters are there, and these limbs can be changed. It is a modular device. So, see, first of all, a little gap here, and then you see he is leveling this, and for leveling it we have some other arrangement. Right now what seems to work best is we have a draw, and then he adjusts this what I call operating lever, and the draw, it sits on that well. Can you see here? That makes sure it is level. Once it is level, after the bending, limb is formed well. After it is formed, he is taking a dry square and checking that we have a perfect 90 degrees. Can you see here? It has been done twice. Other direction also is checking this, and now basically the job is ready. Now you see here, if we have done the calculations right, seen that now we have taken the inside dimensions, then we have added the extra bending elements, that is 0.56, then the machine has been what you call set properly, and a limb of 20 mm, presto, we have it. Good. This looks a little like, is it not a technician's trade? No, it is not a technician's trade, not all a technician's thing. If you want something to work, you need to be familiar with it. Same thing with the 30 millimeter limb, same thing with the 50 millimeter limb. It did not focus, say all the limbs have perfectly meshed. So, what I wanted I got. And why this? This is, the focus is, this is a very complicated way of doing it. One of the first thing is, you have to determine the actual part what we want, dimensions of the part, which is where I feel our CAD, any CAD system will work. Second part of it is how to make the parts fit properly. So, the next I will go up. To calculate this is that bending allowance, we have any number of these formulae which are mentioned in the web. You have seen this. In this particular case, we have the inside bend radius, and we have a material thickness. I do not know, here it says meters or it is millimeters. The important thing we end up with is funny K. Ha. Where do we get the constant? Like all other engineering calculations, our part comes to how do we determine this K constant. So, if you go into the thing, I couldn't unfortunately save these things. A lot seems to depend on where exactly does this so called neutral axis end up with. So, we have still a problem. In this thickness of T, where is the offset of the neutral axis, which is not at all so easy to determine. Hence, it is treated empirically, and depending on the type of fabrication and machinery and so on, generally the shop people are familiar with it. It just takes you know that we just use it in one of our these things, and then try to do what best. You see here we have a little problem here. In this case, the neutral axis is shifted to the inner line. So, in this case the bend elements changes dramatically. Yeah, this is what I was looking for, finally got it here. While that was a folding machine which I had shown you here, this is a air bending using a punch and a die. The top side is where the punch comes and the bottom side is where the die sits. In this case, it is loosely called air bending because there is a small gap of air and then it is allowed to freely take any shape you like. So, depending on the details of this particular thing is called air bending. Some places both sides touch the thing, that such a thing is called coining. So, what happens in all these things are, one limb gets compressed, another limb gets expanded and there is a neutral axis shift. This neutral axis shift has to be determined by practice. So, and there are a large number of tables here. So, we have this generic K factors. Mind you, the word generic again reminds us that we need to make specifically for our particular operation. Okay. So, in this case it says from air bending, which I just explained, bottoming meaning it just touches the bottom, coining saying both sides are squeezed fully. So, up to a certain thickness where the radius is 0 radius means it is a sharp angle, to one thickness this is what is used. So, generally we are in this area. Mind you, it is a K factor, it is not the bending elements directly. So, in the case of steel, we know generally most steels come in the work hardened condition. Work hardened condition means as it is rolled or as it is done, it comes into a thing. Very rarely any annealing or such operations are carried out. In some way very strange specific cases, a little bit of aging is carried out, but never this. And in the case of aluminum, depending on the content of magnesium and silicon, the material property changes from soft to medium and some of them can be hardened all the way up to this. So, this K factor keeps changing, and which I have told you earlier, it is a lot dependent upon the specific working conditions. Here he has given pictures of, say, what happens here. The one outside you can clearly see has got stretch, the one inside there is a compression, and whenever we are talking about any of these further operations, we need to be familiar with this. Oh, it is not clear, it is nothing, it is just that various sources I have tried to take it, and at this point today I would like to stop. Okay, thank you.